an undergraduate at IIT Bombay and is soon going to start graduate school at MIT. So we did this over the last. We've been doing this over the last 1.5 years. So here the problem. So the problem is well studied and it's simple to state. You're given a convex body, and you want to sample a point approximately uniformly from the body. So there are many questions about how the body is given and so on. About how the body is given. So a natural way that the body could be given is that you have a membership oracle. So you can query the oracle with a point. So you have a candidate point and you ask whether it is in the body or not. And you're also told something about the body, that it is like its whereabouts. So you're told that it contains a small some ball of radius r, and it also is contained in a ball of radius big R. So this basically says so if the ratio of capital R by small r, if that is small, that tells you the body is not like a thin slice. It's really it's not close to being smaller dimension. So that ratio will play a role, but that's important. Another important case is polytopes. So here you could have another reasonable representation that it could be given by specifying a set of linear inequalities. So there are many reasonable ways of specifying a body. So this specification by a set of linear inequalities is stronger. It implies the membership oracle clearly. So that's just to say like how the body would be given. So we'll always assume that the membership oracle is known. And what we want to do is to produce a sample that is close in statistical distance to the uniform distribution in K, and we want to do it fast. So fast here would mean that we want to be polynomial in the number of dimensions. N is always going to be the number of dimensions. This aspect ratio, capital R by small r. So this is the ratio of the big ball that contains the body versus the small ball that is contained in the body. And log of 1 over epsilon. So this log is important. So log of 1 over epsilon. So that's the usual mixing time kind of requirement for Markov chains. That you want to get to within epsilons because it's statistical distance, and the runtime should scale as polynomial in the log of the 1 over epsilon. So any questions about the setup?
I'm still. Can you again explain me this poly notation?
Yeah. So this means it has to be a polynomial in all three parameters. So some fixed degree. Yeah.
Okay.
I had one question here. I had one question. So the B2 refers to the L2 norm ball, is it?
Yes. Yeah.
Okay, thanks.
Yeah. It could be other balls also. So the point is that something of this kind is needed. It won't. I mean, it will change the polynomial later if you use other norms. But basically, the point of the aspect ratio is that makes sure that the body is not like a thin needle. So if you have a thin needle, then the small r will have to be very small. So capital R by R will be very large. So that's it. Okay. So there are many reasonable attempts. So there's rejection sampling, for example, but it's easy to see that it usually will just in high dimensions, it will not be good. So the usual way is to actually do random walks. So you start at some point in the body and do a random walk inside it. So some random walk. And then you ask how long does that random walk take to come close to the station distribution. Many such random walks have been studied. In fact, the first random walk for which polynomial sort of polynomial mixing was proven, or such an algorithm was given, was by Dyer, Fries, and Cullen. It's 1991, and it was based on doing a random walk on a uniform grid and then doing some post processing on top of that. Probably a more natural walk, which was analyzed slightly later, is. So I think it was actually slightly. I mean, the full algorithm was slightly later. Is this ball walk, which is, as the name says, it's exactly what it is. So you fix a radius, some radius of the ball, let's say b, and what you do at each step is that you draw the ball of let's say the L2 ball of radius b around the current point, sample a point uniformly at random from it, which you can do because that is an easy problem. And then if that point happens to be in the body, you move to the point. If it does not happen to be in the body, then you stay where you are. So that's the most natural walk, random walk in some sense. Another one, it's actually even older in terms of when it was proposed, is the hit and run walk. And so this may be best to set a picture. So you're at a point, you draw a random chord. So by random chord, I mean that you pick a direction uniformly at random from the unit sphere, and you draw the chord in that direction of the body. And then you pick a point uniformly at random from the chord. So this can be done using the membership oracle. So you can figure out what the length of the chord is by doing some kind of binary search on the direction, and then you can do a uniform sample. So and then you move to that. So that's hit and run. And this also has been analyzed quite extensively. A related thing, which also actually is equally old, probably older, is something called coordinate hit and run, which again, as the name maybe suggests, it's very similar. So now, instead of picking a direction uniformly at random from the unit sphere, you pick it from the one of the n coordinate directions. You pick the direction, and again, you do the same thing. You pick a point uniformly at random on that chord, and you move to it. Okay. So there are also some other like, so these are all, so there are also some other walks like Hamilton and Monte Carlo and its relatives. So that I won't be talking about. We'll be focusing mostly on this in this talk on coordinate hit and run and its relatives. So any questions about these?
The coordinate hit and run case will be restricted to a grid, right? And then in that case.
No, because it's
I mean,
continuous.
it will not great, but I am sorry, not great, but it will have a very strong bias towards. I don't know. Maybe I'm wrong.
No, it's reversible. So it has the uniform. It's reversible with respect to the uniform distribution.
Okay, fine. And why is it called hit and run?
Yeah, I don't know actually. I don't think the original people called it hit and run. I think the Lovász's paper maybe. I don't know who was the first one to call it hit and run, but I think that roughly the idea is that you hit, as in you pick the direction, and you run because you can move very far. So that's the advantage of these walks, that you can potentially move very far in one step. Ball walk cannot move far in one step.
Maybe
this is important. We'll see.
Maybe this is a baseball or cricket analogy.
Oh, it might possibly be baseball. Yeah, may possibly. Yeah. I was thinking of slightly less salubrious things.
Oh yeah, I see. Hit and run. Okay.
Yeah.
I see.
I see.
Okay. Yeah, but yeah. So the point is, so the difference is that it can move very far in one step. Okay, so both of these can move very far. So so what we want is fast mixing. So we want to get to the stationary distribution quickly, and we cannot always hope for rapid mixing. We start from arbitrary state. So we'll see why. And so the question we'll ask is, what are the appropriate? So one question to ask is, what is the appropriate starting state? And one maybe slightly more sophisticated version of asking it is to ask, what is the effect of the initial density? Maybe the initial density is not just a point. Maybe that is already slightly randomized. You can do that.
Sorry to interrupt. I'm not a probabilist. I don't know what mixing means. Like
mixing.
Fast or rapid mixing.
Yeah, mixing means exactly what I said on the first line. So we want to get within epsilon statistical distance to the uniform distribution. So the random walk has a distribution. So initially there's an initial distribution. Then I take one more random step. So the distribution changes. Then I take one more step, the distribution changes again. So it keeps changing. At every time there's a fixed distribution. That is the deterministic evolution. And I want, And the mixing time is basically, so fixing an epsilon, the mixing time is after how many steps am I within epsilon distance to the target distribution. Okay, so one thing is, one could imagine that there is some dependence on what the initial density looks like. And we'll see that one way of quantifying this is looking at the density of the initial probability distribution with respect to the target distribution, and saying that it should not be too concentrated. So the density should be bounded above by M. So this is called M-WOM. That's just a term. So M-WOM initial state means that the initial distribution has density that is bounded above by M times so the Redon-Nikodym derivative of the initial density is at most M with respect to the target distribution. Okay, so in particular, if you start with a single point, then the Redon-Nikodym derivative is unbounded. So that is not M-WOM for any finite M. Okay, so starting from a single fixed point is not. Okay, so in terms of our mixing time bound, so if the mixing time bound was polynomial in M, okay, then we will get rapid mixing only when the M is itself polynomial in N and R by R and so on. So we will have to make our initial density itself pretty good. It will have to be like not so far from the uniform. What we would like is so-called cold structs, which is that the distribution on M should be logarithmic, so polylogarithmic. So then you could handle M that is exponential in N. And that is easy to produce. So one way of producing such a M is because you already know this capital R, small r balls. For example, you pick a small r you pick a point uniformly at random in a small R ball, that already achieves this essentially, polynomial in n and capital R. So, so that is easy to achieve, but warm start it's not clear. So there are ways to achieve it, but they're non-trivial. So, and usually if you get a mixing time with this kind, of the second kind, where there's a polylog dependence, you can often massage it to prove rapid mixing from a single point also, from a starting point. Although it's not immediately, does not follow by translation, because m is infinite for a single point. The way you do it is by saying that you start at the point, and within a small number of steps, your density has sufficiently diffused. So it is, and then you plug in this result. Okay, so that's the story, and so let us just say what is known about these kind of things. So for the hit and run walk that I talked about, not the coordinate version. So the warm start was proven by Lovász. It's a very nice paper using with nice connection to geometry, so he proved it with just warm start. So he proved a mixing time where the dependence upon this warm parameter was polynomial. And the cold start actually took much longer. It like 5-6 years later, and it based on based on the improvement of that the geometric results that Lovász was that was the heart of Lovász's warm start proof, and that was in 2006 by Lovász and Vempala. So we'll come to these terms later. So the one difference between the two was something called a conductance versus X conductance torment. I'll define these terms very soon. But just yeah.
So what is n here? Is it number of iterations?
N is number of dimensions, and this is written is the number of iterations needed. So the number of bound on the number of iterations was growing polynomially in the dimensions r by r and m for the initial proof.
Okay.
And the later one improved the dependence to polylog in the m.
Okay.
So I'm not worrying about a degree of n here. Of course, these proofs actually say what the degree is also. These are not existential proofs, they actually put the number. But for this talk, I'm not worrying about that. So for coordinate and run, this is interesting because actually when it was proposed in 1984, that paper was sort of more like exploring various implementations and seeing which ones look good. In numerical implementations, the coordinate and run seems promising. It also it's intuitive because especially if you're in a polytope, it's easier to check coordinate directions because each inequality is in terms of the coordinate variable, so you can check how much can you change the variable. So the figuring out the chord is easier. So these kind of, because of reasons like this, it seems to be useful in implementations, and it is part of many packages and so on. But mixing time, bounds for which were somehow not known until very recently. So there was the two papers appeared in the archive around the same time, within 2 days of each other, with different proofs of fast mixing from a warm start. So one was by Santosh Vempala and Aditi Ladda, and the other one was me and Hari. And the cold start thing still remained open. So we had a mixing time bond of this kind. So my pointer is visible.
Yes.
The mouse, yeah. So these two papers had bounds of this kind here, and this finding a cold start bound was missing, and these proofs seem to be quite different. I mean, they couldn't become as nicely geometric as Lovász's original proof. So this strategy needed seemed to be different. Okay, so why worry about warm and cold start? So I already alluded to this a little bit. So achieving a warm start is not clear at all how one does it. It can be done. The TIFR CAM paper already did some version of it, and but the cold start is trivial to achieve. As I said, when you have the capital R, small r, just sampling uniformly from the small r achieves it. So, and the other thing is that you won't want actually ideally to just mix from any point. You do not want any. Just for aesthetic reasons, you just want to run the walk from arbitrary point in the body, or at least point is somewhat inside the body, not too close to the boundary. And the cold start doesn't immediately give that, but often those results, as I said, can be massaged to give that also. Okay, so with that, I'll just go to the results.
I have a question. So in this starting from a point, you seem to be distinguishing something in a compact set versus something in a boundary, near a boundary. Why is that? Because from what I understood, the hit and run scenario, it shouldn't really matter, right?
No, if you're very close to the boundary, what can happen is that, for example, your convex body might be like a pointed cone.
Oh,
and
I see.
you could be very
might be limited. I see.
Yeah.
I see.
Yeah.
Okay. Yeah. Thanks.
I mean, so the heated it doesn't really matter. So you even if you are exponentially close to, like, as long as you're like something like e to the power minus n away from the boundary, it works out. But if you get very, very close, like doubly exponentially close something, then you can get stuck.
Thanks.
Okay. So that's so here the results. So actually, what we do first is we define a different class of Markov chains. But actually, they're all similar to each other, and prove a fast cold start mixing for them. These are not coordinate in or dependent like Markov chains. They are sort of more like chains with countable state spaces. And then we use those mixing time results for those chains to prove something for coordinate invariant. And these chains are based on a very classical construction of Whitney, of so-called Whitney decompositions. So what the Whitney decomposition does is that it decomposes this body, in any open set, in this set of collection of dyadic cubes, and with a certain special property. So the point is that what you want to do is that as these cubes come closer and closer to the body, to the boundary of the body, they want to become smaller. The reason is that you want that the local geometry of these cubes should appear similar, like up to scaling at any point. So what you want is, like, you want to decompose the body into cubes, but somehow with the property that that if you look at any one cube and you look at its neighbors, then it does not matter how close that cube is to the boundary, their local geometry looks similar. So in what sense? In the sense that the number of neighbors, how much smaller or how much bigger they are, that should not be too different from what it would be in the deep interior of the body. And this can be achieved. And so basically what the condition I'm talking about boils down to these two things. So side lengths of any two cubes that are neighboring, like which share a facet or partially share a facet, they should have side lengths that are within a constant factor of each other. And that factor should not change as you come close to the body. So that's, let's say, 2 of each other. And because they're dyadic cube, that basically means that either it's half or it's double or it's the same. So just 3 possible choices. And this more or less requires then that every cube has its size or its side length close to roughly proportional to its distance to the boundary. Okay. So in fact, yeah, so that also implies that for any point inside the cube, the distance of the point to the boundary is within a constant factor of the diameter of the cube. So this can be done for any LP now. So this is a classical construction. I mean, this is not just one construction. There are many such constructions, and with the general idea remains the same. So we use one specific one like this. It's easy to create, and it can be done lazily. So you don't need to prepare this infinite set of cubes in advance. You can under reasonable sort of assumptions, given the body, you can actually given a body and the point inside the body, as long as the point is not on the boundary of the cube, you can tell which cube it is in. What's the center of that cube? What's the side length of that cube? You can just calculate for any point. So this decomposition just exists sort of abstractly, and to use it, you just at any point you just figure out which cube you are in currently. And our Markov chain is going to be on these cubes. So it's not going to be on the body itself, but on the cubes. Okay, and now it's a sort of a Markov chain with countable state space, because these dyadic cubes form a countable set. And we want it to somehow still relate to the random walk on the body. So what we will do is that each cube will have a probability. So the target distribution should be close to the uniform distribution on the body. So the correct target distribution, therefore, has to be the one where the weight of each cube is proportional to its volume. So then one way to sample uniformly from the body is to first sample uniformly from this distribution and then sample from the cube. But sample from a cube is trivial. I mean, you just sample each coordinate independently. So and if you are close enough in the statistical distance to the for this countable distribution, and then you do this thing, you also get close in statistical distance to the body of the station distribution on the body. So this is fine. So what we want to do is the Markov chain, which has, so this is what I will say. So we want a Markov chain on this set of cubes for the body, where the stationary distribution on any cube is actually equal to what it would have been if I thought of that cube in the uniform distribution of the body, which is just the volume of the cube divided by the volume of the body. So that is the chain we want. Okay. And this chain is actually not, so, I mean, yes, you can design it easily. It's like, it's just using usual metropolis or some such rules. So the rule one can use, for example, is the following. You are currently in a cube. You first pick a point uniformly at random on its surface, which again can be done easily because the surface is just, I mean, it's just a collection of smaller dimension cubes and they're all the same volume. So it's easy to sample a point uniformly from the surface. That point now is on the surface. So with probability 1, there's exactly one more cube which shares that surface, even partially. So that is our candidate cube that we want to move to. And we just do an accept reject thing now. So we accept this. So our proposal is to move to this cube. So we picked a point uniformly at random on the surface that suggests the neighboring cube to move to, and we accept that proposal, which is with a metropolis filter where the probability of acceptance is proportional to the ratio of the side lengths. So if the side length of the target cube is bigger, then we just move. I mean, up to with probability half. So half is for laziness. So for technical reasons, it's always good to make the Markov chain lazy, where with probability half, you do nothing. With probability half, you do whatever the chain says. So that's just from reasons of getting positive eigenvalues and so on. So let's not worry about that. So just this term. So the point is that apart from this half, so if you propose a larger cube, you just move to it. But you could also move with some probability to a smaller cube, which would be half the length. So remember that in this setup, all cubes that you will ever propose are within a side length. So either the side length is equal or 1/2 or twice, because they're all within a factor of 2 and they're dyadic cubes. So the transition probabilities are not hard to write. So in this case, this is a Markov chain with discrete states, and this is a transition probability. So this factor goes here, and then there is a factor. This basically tells you what is the probability of actually proposing that cube, because you have to pick a point that is this is the part of the surface of Q that is actually shared with Q2, and you're sampling uniformly from the surface. So this is the Markov chain. And the P here just says which of the, remember that this decomposition depends upon which norm you're using. So for each norm, you get such a decomposition, and for that decomposition, you get this chain. Okay. So that's the Markov chain. And the main technical theorem is that this Markov chain actually does mix fast. So I'll change the regularity condition here slightly, but up to polynomial factor doesn't make a difference. So if you have the body K is contained within R times the L infinity ball, which is just the big cube, and small r times the LP ball, then from any M worm start, this capital M random walk on K has this kind of a mixing time. So how do we make it into a random walk on K? Well, it is easy. You are at a point, you find the cube it is in, and you just say that my current state is just a uniform distribution of this cube. So now you can think of it as a walk on the body itself.
I had a question.
Yeah.
Is the convexity of the body very, very important?
Yes.
I can just imagine that if there's a bottleneck, there'll be a problem.
Yes.
But suppose it's non-convex, but at the same time, you have some criteria which says that you don't have a very large bottleneck. You would get similar bounds, I guess.
So that will have to be very done very precisely. So so the question is whether there are bottlenecks or not, but it sort of becomes begging the question kind of a thing, because the proof of mixing is basically to prove that there are no bottlenecks. So the proof will be that in a convex body there are no bottlenecks. So the question is, what are the other cases where there are no bottlenecks?
Right. So one would hope for a geometrical criteria on the body. For example, convexity is a obvious geometrical criteria.
Yeah.
But
so in fact, the proof itself will go through a geometric isoperimetric inequality. So any body that will have
that's what I wanted.
So just to follow up Nishant's question, so one way to do this is you take maybe a defining function of the boundary.
Yeah.
And you look at the Hessian, and then you say that, well, if it's positive, we know it's convex, but what if you allow, say, small negative eigenvalues? That I think that should translate to lack of bottlenecks, I suppose.
So I think you could do something like very smoothly having a bottleneck, right? Like you have a ball and like
not a rapid drop. Yeah.
but even that would be a problem. Like, so if you have the kind of thing I'm thinking is a ball, and it smoothly goes into a small pipe, and then again there's a ball. This should also be a problem, I think.
Yeah, and the Hessian won't detect that. Yeah,
Yeah.
small eigenvalues won't detect that. Yeah.
So is the algorithm saying you can only move to the neighboring cube, not
Yes.
jump?
Yeah. This algorithm is not jumping around. It's not like you can run it.
So then would not it be slow? I mean, if you are towards boundary, then from
Yes,
the
actually, yes.
boundary.
This is actually one of my open problems. So, so far, all the proofs we know for coordinate element do not actually use the fact that it is jumping around. They actually just use the fact that it can move close by. We don't know how to use that fact. So we could potentially improve the running time by a lot by somehow exploiting this long movements. By the way, this Markov chain can move long distances, because if you're far away from the boundary, then you have these huge cubes, right? So, like, remember, so if you see this picture, if you're very in the deep interior of the body, then your steps are actually very long in geometrical, even though you're moving to a neighboring cube. But as you come closer and closer, your steps become smaller, which is a good thing also, because there you cannot jump very far. Like, the ball walk actually is a problem because of this, because it doesn't care about how close to the boundary it is. It still tries to sample from the same ball. But then coordinate doesn't have the problem. It can move very far even from when it's close to the boundary. But we can't seem to exploit that yet. And exploiting that is probably the way to prove. So it's the current mixing time bond we have, I think, is certainly not the correct mixing time bond, in the sense that one would expect the numerical evidence is that it's much faster than what we can prove. Okay, and this would be based on something called the conductance. So we'll come to that. And as a corollary of the conductance bound, which I'll come to, we also prove a similar mixing time bond for the coordinate run. So again, this thing I've changed slightly. So we have a convex body, which is now, instead of 2 ball, I'm writing the infinity ball. It's easier to write in this way. So it contains the smaller side, or 2r side length cube, and it's contained within the capital 2r, 2 capital R side length cube. Then from a M-Wormstadt, again you have a polynomial mixing time with a logarithmic dependence upon the Worm parameter, and this can also be massaged into a mixing time from a point, as long as the point is somewhat far from the boundary, and that's not very far. Like e to the minus n is capital R is a scaling, and that times minus. Okay, so those are the results. Any more questions about the result? Actually, maybe I'll just say. So yeah, just to recall, to put it in context of the previous work, previous result showed Wormstadt, as I said, dependence on capital M was polynomial rather than polynomial log, and they were based on something called S conductance lower bounds, whereas these are based on so-called conductance lower bounds. So we'll come to that. And what the way of this proof works is actually interesting. So we actually take the proof of Lovász and Vempala, the S conductance proof, and we show that using what we know from this multiscale chains, this MP chains that I was defining earlier, we can extend that proof to prove a full conductance bound. So we'll come to what the difference between S and conductance is. And then the result for coordinate just follows the corollary of the conductance bound for one of these M chains, so the M infinity chain, the one corresponding to the L infinity.
Question?
Yeah.
What is multiscale change?
Multiscale chain is the chain. I forgot to say, this is what we call the multiscale. Multiscale because the scale, it has a different scale depending upon where you are in the body.
No, because I was when you had defined this, I was a bit worried that you would put the entire box as one single dot, but actually you are thinking of this as uniform distribution on that itself.
Yeah.
So otherwise you will end up spending a lot of time on the boundary, and you'll sample the middle. But you're already sampling the middle because
and also most of the mass is at the boundary.
Yeah.
Actually, this was going to be related to a question I had. So, what kind of applications do you have in mind? Because for a lot of sort of problems in analysis where geometry is involved, it's typically the boundary that you're interested in, or near the boundary, right? Inside compact set, often things are easy to handle. Yeah. So why is it that you want to have a uniform kind of a sampling of the entire domain?
Yeah, so these kind of things come from applications in algorithms. So sort of like so for example, in this biology kind of applications, I think what happens is that the interior points in the polytopes are basically all allowed probability distributions. So it's like It's like some of these Bayesian inference kind of things where you're trying to sample a probability distribution uniformly at random from some constraint set.
I see.
And the set is described by a Politov constraint. So these are the kind of situations.
Thanks.
Okay. So yeah. So in one word, the advantage of this multiscale thing for coordinate comes from the polygon. Is S conductance will come to. It needs to throw away some parts of the body very close to the boundary. So we'll see what it means. So it basically has to say some parts of the body are just incorrigible. We can't use them. We have to throw them away. And that causes this loss from log m to m, to polylog m to log to poly m. And this advantage of this multi-scale thing is that you don't have to do that. As you come close to the boundary, still your geometry looks the same as what it was in the deep interior, and so you can still work in the same way. So we'll see how this works out in more detail very soon. So yeah, so some small primer on these terms I've been talking about, like conductance and S conductance and so on. So the goal for our sampling, as before, is to choose a random walk with the appropriate starting state and quickly converge to pi. That's just a recap. So we want within epsilon total variation distance in time that is polynomial in n, r by r, and log 1 over epsilon. So as I said, starting from some starting states can be bad. So one example, I think, maybe I'll do a picture. So we'll see a picture. I don't know. Yeah. Wait, I thought I had a picture. Okay, we'll see a picture slightly later. So this ball walk, for example, it can get stuck for a very long time if it's very close to a corner. So the same corner thing. I'll show a picture of that later. And so the question is, what is an appropriate sort of fast mixing? So that's the thing we want to answer. So there's a nice theory of this in terms of conductance, which also has a nice geometric interpretation. So for that, there's a lot of symbols here, but they're all very simple. So define the ergodic flow of a random walk out of any set. So that's this psi w is the ergodic flow of the walk w out of a set S inside the body. And what is this? It is exactly that I first sample a point from the uniform distribution, and then I take a step. And this ergodic flow is the probability that the point I initially sample lands in S, and the point that I sample next lands outside X. So it's like sampling an edge that is crossing S. So there's a probability that when you sample X from WK, then X lands in S, and when you take the walk from X, it does not land in S. The walk also is random, so that this is also random variable.
Should I think of it something like a Cheeger constant?
Yes, it's exactly. Yeah. So Cheeger constant has to be related to this, but they are related. So we'll see. Yeah. So yeah, but there's a very strong connection. So the conductance is not defined as the conditional version of this. The conductance of the random walk is just the conditional version of this. So condition on the fact that I landed in S when I first sampled the point, what is the probability that I land outside S after one step of the walk? So this is more like a sphere. And or rather the second line here. So what is the conductance of the walk itself? Is the conductance of the walk on a set. The conductance of the walk is the worst possible value of this. So one can imagine that if the walk is able to escape any set, it should mix fast. Or at least if it's not able to escape some set, then it should not mix fast. That's like a bottleneck. That's your bottleneck. And this is sort of capturing that. So the conductance is the smallest possible value of this over all sets. And you have to only go to the sets of size half, because that's just for this technical reason. I mean, if you have the whole body, of course, you can't move anywhere else. So you stop at half. And anyway, S and S complement will have the same. Okay, so this high conductance, so this is sort of an analog of one side of Cheeger's inequality, conducting spectral gap to the conductance. So in these settings, so this is this form it appears in Lovász and Vempala. So one can show that if the starting density has the initial density has electron-Nicodim derivative at most m, then after t steps of the walk w, you come very fast. So your total variation is m times exponentially small in t, so e to the power minus t times conductance squared by 2. So the spectral gap is roughly like conductance squared. Well, it's not exactly like that. It's like thinking the spectral gap is at least conductance squared. So that's one side of the Cheeger symbol. Okay, so if you have a conductance bound, we get fast mixing for free. So we want to prove these conductances. Okay. So the high conductance will also be seen as a statement about isoperimetric, as you already mentioned. So basically, sets with a given volume, which is fix a volume, they should have at least a certain surface area. That's what having a high conductance means. So if I put a set, I just put a lower bound its volume, and it's like not too big. It's like has to be less than a half. But then after that, if the conductance is T or whatever alpha, then the surface area should also be about alpha times it. So this one can interpret as a surface area statement. Okay, so and this thing goes beyond just this word. So actually, the proofs of high conductance for this convex body sampling often go through actual isoperimetric inequality for appropriate metrics, and so we'll have to do something similar here also. Okay, so so one can expect, for example, that small sets will have large conductance, but this can be hard to prove, and this can be for two reasons. One is just technical reasons. So as I said, original proof of Lovász for hit and run, not point and run, actually only had fast mixing with warm start, and that was actually because of this, because the conductance that bound that Lovász's paper proved had conductance decaying to 0 as the set size decayed to 0. So you could only prove high conductance for large enough sets, which is a bit counterintuitive, but that was there. And but this was a technical limitation in the sense that later work by Lovász and Vempala removed this. But this could also be for fundamental reasons. This might be a property of the walk itself. So there might be some small sets which are close to corners where the conductance is small. So here is the picture, for example, the ball walk. So if you are at this point, which is very close to a corner, then you have to be very lucky. You have to so if you're doing the ball walk, you'll pick a point in this blue set, and you have to be very lucky to land in this small sliver to make any progress. Mostly you'll just be sitting there. So for that, like, I mean, this thing has a very small volume because it's close to an apex, but still the conductance can be very small. So this can actually happen. So to get around this, Lovász and Sigurnos also defined a notion called S conductance, where you say that, okay, you neglect those small sets. So you say that the conductance is now defined as the ergodic flow divided by essentially the volume minus S, but you only now don't look at all sets, you only look at those sets of volume at least S. So the small s is the parameter. And then if you can prove something about S conductance, so it's like you're throwing away part of the body and it comes at a cost. So if you have only an S conductance bound, so if you can, so if you have this S conductance bound, then what you get is that the total variation distance now is M times S. So this linear term in S is already there. And then again, the exponential decay. But this will dominate basically, like eventually when this becomes very small. So if you only know that the S conductance is not, I mean, if it is only decaying like proportional to the size of the sets, then you, from this, you can calculate the mixing time bounds you get are polynomial in it, not polylogarithm. Whereas conductance gives you, whereas if you have conductance bound, lower bounds, then you immediately get from the previous thing I showed that the mixing time is logarithmic. N. So yeah. So basically, so just to recap, the initial point has probability distribution. So if M warm start, and if you only have a S conductance bound where the S conductance taking the size of a set, then we only get a warm, this kind of a mixing time, poly in M. If you have a conductance bound, then we want this. Then we get the thing we want. Okay, and so for warm start, so yeah. So this is just recap. Okay, so this is where we are. So we want to prove this conductance. So yeah. So we have already seen some of these examples. But if there are any questions, I can.
Yeah. So in the rough picture of the proof that you had given.
Yeah. It's not a proof. Yeah, it was more.
There's like the technical challenge that is basically in the that is a small conductance region.
Mm-hmm.
So where is the cold start problem appearing in the proof? The problem, in the sense like for the warm start, the proof seems to be like that is the argument that you are giving. But for the cold start, where is the problem?
Where is the problem? I mean, in the sense that you don't have a conductance bound. So your starting point might be this, or it might be very like so this set is exponentially small.
Right.
Okay. And so your cold start set might be completely focused, like the distribution might just be here. Right? Because cold start allows you to do that. The warmth required is only exponential.
I see. Okay. Thank you.
Yeah. Okay, so how does our proof work? So we want to prove this kind of mixing time bound, and basically it goes by proving a conductance bound. So I'm talking about the multiscale MP random walk. So essentially what we want to prove is this thing here. So we want to get a conductance bound, which is inverse polynomial in n at most, and this and r by r. Okay, but it has to be a conductance bound, really. Okay, it can't be S conductance. So at high level, the proof structure follows many of the results in the area. So you have to first do a conductance bound. So you first try to find an isoperimetric inequality in some appropriate metric measure space, which implies the conductance bound, and then you prove the isoperimetric inequality. That's or you get someone else to prove it. I mean, you find the distance. And so the question here is, what should be the distance and what should be the measure? Because we're talking about a metric measure. The measure is sort of fixed for us. It's a uniform measure in the body. So the question here is, what is the distance? So what distance should we use? So the point is, so to get some intuition about what the distance should be. So notice in the chain, when you're inside the body here, you take steps that are of this length. But when you're here, you take steps that are much smaller. But somehow the local geometry has not changed. I mean, the cube, for the perspective of this cube, looks similar. I mean, they are roughly neighboring cubes are also either size of. I mean, they're either the same size or size half or size twice. So relatively, nothing has changed. So, and in some sense, the chain is still work in progress because it is moving to adjacent cubes. Of course, in the Euclidean distance, that's not same progress as here. But we want to somehow say that this progress is similar to that progress. So to do that, we want a metric that will expand those distances close to the boundary in length. And so one can do that, for example, with this kind of a metric. So what I would want is that any length element at x should be sort of like the L infinity length element, but 1 over the distance to the bound of the point to the boundary. So scaled by 1 over the distance. So as you come closer and closer, you are so L infinity, because of course you're doing the cube, so L infinity is a natural notion. And but now we want we basically want it to be 1 over proportional to the cubes, because these cubes themselves have dimension, which is remember the cubes that when you come to within distance d of the body, the cube has diameter that is proportional to this. Right? That was one of the properties of this decomposition. So this is the kind of metric we want. So this is of course written slightly in a non-rigorous notation. So the way, so it's a more sort of formally, what you want is that the length of any curve should be given by this. So the length of any curve inside the body should be given by this. This is the same thing just written correctly, and then the metric is just to take all differentiable curves and take the infimum. So that's the metric. So this is the metric we use, and the main technical result that you to prove is an isoperimetric inequality for this metric. So it says the following, that you have a body which has again this capital R, so it's contained inside. So it's the same setup as the mixing time result. And there's some delta, the distance parameter that is given. So this is like a integrated isoperimetric inequality. Rather than for the surface area, we'll talk about like the thickness of the separating side. So you separate the body into 3 parts, S1, S2, S3, where S1 and S2 are separated by delta distance in this metric. And we take the S1 to be the smaller set, or S1 that is of size less than half. So that's usual. So then the thing that is separating S1 and S2 must have volume that is at least proportional to the distance. So that's why it's like an isoperimetric inequality. So you can imagine that you divide by delta and take the limit. So that's like a surface area. But yeah, we won't have to go do that. So delta times the volume of phi k, and times something that are reasonable. They're polynomial, so inverse polynomial in our parameters. Okay, so 1 over n and 1 over the aspect ratio, and some constants. Okay.
So the sets that you kind of care about are like, I'm guessing that this isoperimetry is for a general measurable set. Do you really care?
Yes, because if I don't get the conductance for arbitrary sets, then an adversary will just choose that set. That will be the bottleneck set.
I see.
Okay, so maybe in the 10 minutes or so I have remaining, what I will do is I'll just say why this isoperimetric inequality will imply the conductance form. And maybe I will skip the other 2 parts, which is to prove the isoperimetric inequality and to go from the conductance bond for M infinity chain to the conductance bond for coin. Right? So what we'll do is, or we can do one of the other 2 also, but I think this one is maybe to at least complete the story, just to say how will this isoperimetric inequality imply the conductance bond that we want. Okay. and also maybe give a more, so I give a slightly hand-wavy description here of why this is the right metric in this picture, but we'll give a more formal reason why that's the thing. So we want to prove a conductance bound. So we want to say the ergodic flow of any set is large compared to its volume. It's not too small compared to its volume. It's proportional to its volume. And the proportionality constant is not very small. Okay, so we start writing down the ergodic flow, and we know the Markov chain, same Markov chain. So it's picking a point on the surface, then moving to the neighboring cube, if based on this metropolis filter. So it's so that is not so hard to believe that basically the ergodic flow out of a set S. So what is a set S? S is some collection of cubes. So it's some collection of dyadic cubes, where the total volume of those cubes is at most half. And you write, and the ergodic flow looks something like this. So up to this polynomial factors, it looks like the surface area of, so you go over all the cubes in the body, and only those cubes in the body that actually are on the boundary of S, in the sense that one of their surfaces is also a surface of S. I mean, if the cube is contained inside S and that all its neighboring cubes are also in S, then that cube is not going to contribute to the ergodic flow, because any movement from there will be within S. So only those cubes can contribute to the ergodic flow which have at least some surface that is also a surface of S. So this is those guys, and they somehow contribute roughly proportional to their diameter. This comes from the fact that there is this surface area term. So yeah, so this is, so I mean, I wouldn't I mean, this is easy. I mean, there's nothing going on here, but I just want to take say that like this is reasonable, like at least dimensionally, that this is what you get. Okay. Okay, so now at this point, we use some geometric thing. So we have this surface area here, and we want to relate it to, I mean, we don't want, so all our things, we would want to work in n-dimensional volumes and surface areas. And usually the surface area of a body is that you take the body and you expand it by epsilon L2 ball, and then take the difference of the volumes and then let the epsilon go to 0 and divide by epsilon, and that's, I mean, divide by epsilon and then let the epsilon goes to 0. That's the surface area. Here, because we are doing something very special, like we are only the things are varying is an infinity ball, and because our q's etc. are also all axis aligned, the same thing works out even for the infinity ball. It does not work out in general, but here, because what you can convince yourself that if what you're working with are like very nice axis aligned sets, then even the infinity thing works for essentially the same reason. Basically, the points that are sort of really that are not in the L2 ball but in the infinity ball don't contribute. They go to 0 very fast as epsilon goes to 0. So yeah, so this is an easy lemma to prove. So now, but that lets us replace the surface area by a volume. So we have this kind of a volume. So you want, for each cube, we want to look at epsilon times the infinity ball. So, but this is slightly strange because for each cube we have this point. What we would want to do is to have, for every point we want to add a infinity ball around it, and that we can do because for any cube we know that all the distances to the boundary are within constant factor of diameter LPQ. So we suggest, so this suggests instead of this kind of extensions, for every cube we look at, for every point we extend it by 2 times epsilon times the distance of that point, right? And this is within a constant factor of the diameter of the cube also. That's what we would ideally like to do in the light of this, but we can do this also without, this keeps it more uniform. And now using this we can get something. So we have this limit here by the previous lemma that is equal to this side. The c times diameter LP just comes because c times diameter LP factor here. And sorry, what is it? Yeah, so this comes from the lemma, and this side here just comes from the fact that because I've chosen a constant c in such a way that if I take this q epsilon, this guy here, this non-uniform one, that one, because of this constant factor thing, because this LPX for every x in q is within a constant factor of the diameter of q, I can choose some c so that this q epsilon is completely contained inside this q plus c epsilon. So that's just so you choose c, so like 10 or something is what that capital C is. So you get this, that what was appearing here is upper bound is at least this kind of a very volume-like looking, like volume, something that looks very much like a volume. So at this point, what we have is the ergodic flow is within some polynomial factors times this lim sup of this volume of q epsilon minus s, where q epsilon is this epsilon extension. Every point is adding a cube around it, which is of length size proportional to its distance from the boundary, side length proportional to that. And that by just changing integral and limit by reverse Fubini. So now instead of q epsilon, I just get s epsilon, because all these q's were just, we're going over all the cube things. So s epsilon is just the cube. Okay, and now we are in a situation where we can use our isoperimetric inequality, because our isoperimetric inequality wanted a partition. So our partition is not natural. We take s and we take k minus s epsilon, and the thing in the middle therefore is s epsilon minus s. So this is our S3, the thing in the middle, and s is the set and s epsilon. So this is just a picture. So s is the red thing and the s epsilon is this green thing, like s epsilon minus s is the green thing, and the rest is k minus s epsilon. And the only thing we need to check is that this GP metric is such that because of this definition of this, it implies that because these distances in L infinity norm are proportional to the distance of the point from the cube, and this GP metric basically shrinks, or rather expands distances by 1 over the distance. So this s epsilon, the distance in GP, that in fact at least epsilon. Okay, so the things outside s epsilon are distance at least epsilon from s. So now this is perfectly in the setup for the isoperimetric inequality, and you plug it into this equation, you immediately get the conductance law. Okay, so any questions about that? I'll probably not go into the other two technical parts and just go to the continuum side after this. And I can go over those after the talk if there is still people are still interested. But any questions at this point?
So just one silly question. So this metric is almost like hyperbolic.
Yes. Yeah. So it is all. So in fact, so in the hit and run proof of Lovász, the metric is in fact exactly the Hilbert metric, more or less. Except that he doesn't have. So the exact Hilbert metric would be like log of 1 plus the cross ratio, and he has to actually use just the cross ratio.
I see.
So that turns out to the monad. So yeah, so this is also like the Hilbert thing, but maybe less comfortable, less elegant.
Okay. Thank you.
So the Hilbert metric sits very nicely with the hit and run, because the cross ratio comes up naturally, right? Because you are drawing this chord and then looking at these 2 points. So it's somehow natural that to think of the distance as the cross ratio, but here it's not.
So I had a question about the metric as well.
Mm-hmm.
So the metric you're using is somehow isotropic, right? It sees all, like it's basically you're scaling like a unit cube.
Yes.
That you can kind of fit in, and then what you can fit in, you kind of rescale it by the distance to the boundary.
Yes. Yeah.
But because you're on a convex setup, would it be advantageous to try a non-isotropic metric where if you're like interior point doesn't matter, but near the boundary, like the normal direction, if it's scale 1.
Yes, actually, yes, that is true. So we have tried that. I think there is some evidence that it might help improve the running time a little bit. So the natural thing, because we're trying to do coordinate-based things like coordinate update, the natural thing is to, instead of looking at a cube like infinity, you at least look at a rectangle, like what is the distance that I have in each direction, and scale like that.
And also you change the coordinates based on the point, right? Like the normal versus tangential, because that's going to give you kind of the maximal capture of the geometry.
So I'm wondering if that will just become the Hilbert metric or something like that. Or not. I mean, maybe not. But here the thing is, because we want to do this, we want to be aware of the coordinates.
I see.
Because we are trying to, ultimately our goal is to get to coordinate directions. The coordinate directions have to somehow be kept special in some way.
I see. So So it's not just the body and the geometry of the body that you're interested, but the initial frame that's given to you, you also want to retain that. I see. Yeah. Then the non-isotropic thing, I'm not sure how to implement that very effectively.
But this cuboidal thing, I think, so we didn't fully work it out, but it seems that can be used to improve something. Or maybe we did work it out. Okay, so so I will, so because it's already 5, so I will not go into the proof sketch. You can describe that later. Maybe I'll say one word. So basically, the proof breaks into 2 parts, and it of the isoperimetric inequality. One part is that this set S. So basically, you have to say this S3 is a large set. this thing in the middle is a large set. There's S1, S2, and the thing that is this slice sitting in the middle is large. So it turns out that you can break into two parts where like there's a lot of mass of the S1 set sitting inside the body, deep inside the body. If that happens, then this infinity metric, the metric I wrote down and the L infinity metric are not really so far because the distance to the boundary is not changing. I mean, you're very far inside the body. It's not like, because all the distances are somewhat large, so they're all within a constant factor of each other. You can just think of it as an infinity metric. And there are like any number of isoperimetric results. You can just plug in something from the literature. The interesting question is what happens when most of the mass of S1 is also contained very close to the boundary. And in this case, we have to use some of an ad hoc version of something called a needle method. So many of these isoperimetric inequalities are proved by something called a needle method, which is also like it's also like often called localization. What that means is that you show that if the isoperimetric inequality had to fail, then a one-dimensional version of it would have to fail. And that one-dimensional version is on something called a needle. So the needle is basically like so basically it says that if the inequality has to fail in the body, then you will be able to find basically a line segment and a frustum of a cone around it, basically like a measure on the line segment, which looks like the frustum of a cone. So it's like exponentially increasing because the frustum of a cone is like, so the radius is going from A to B. And so the corresponding volume is proportional to radius to the power n-1. So it's like changing like that. So you have some such measure that is inside the body where also a one-dimensional version of the inequality would fail. And that you prove by yes one-dimensional calculus argument that cannot happen, and therefore the inequality holds in the full dimension also. So it's a localization in that sense, that there is some needle or some one-dimensional type inequality that had to fail. In our case, what we have to do is actually have to explicitly make these needles. So we have to like take all these, so pick a point, a particular point in the body, draw these needles, and look at these measures, which are like now again similar to these conical measures. And we know that S1 contains a lot of mass close to the boundary. So we look at those needles where actually in those needles also S1, most of the mass is close to the boundary. Those will be a large fraction in those needles. And for those needles, we show that you can find a reasonably large amount of S3 also in those needles. And that's how the proof goes. So in that sense, it's similar to the needle method, but the needle method is existential. So there's a so-called, it's called the localization lemma, originally proved by Lovász and Simonovitz, and then improved by Kahn and Lovász and Simonovitz, which says that essentially for any kind of this, so it's a much more general result. It basically says that there are two integral inequalities, by which I mean things like integral of f is positive and integral of g is positive. If both of them happen on the body, then they will also happen on some needle. And the failing of a coordinate of an isoperimetric inequality can be written like that. So that's, but here we are not using that because we have to sort of actually take all these specific needles and prove it sort of by hand for them. Yeah, I'll probably just skip this part about how to get to CHR. So in conclusion, so what we have is a new family of Markov chains for sampling from convex sets, these multiscale chains. It's not clear how useful they are as implementation. We have not yet tried that, but potentially they could be. I mean, they're also coordinate aligned, so that they have that advantage. That just exploits nice properties of the Whitney decomposition, multiscale classical multiscale decomposition. And the analysis depends upon coming up with this metric, which captures progress of these chains, and then proving the appropriate isoperimetric inequality, and that leads to the conductance bound. And then one can also go back and use the conductance bound for the multiscale chain to connect it to coordinate inverse. So you can basically compare the two chains and show that because the M infinity has good conductance, the coordinate will also have good conductance. So many things remain open. So this was just, I always just worked with convex bodies, but you can ask for more general sampling problems like arbitrary log concave distributions. And it's not clear if multiscale decompositions help for that. Many of the other methods do work, like hit and run sort of is known to work. And to improve the mixing time for a coordinated run. So the kind of runtime, as I said, we get is quite bad. It's like n to the 9 something. That's not what I think people believe is the correct answer. It's numerically, it seems much better. So we don't know, but this method sort of seems like, so we also know that the conductance bound we proved for the M infinity chains is actually tight. So there are sets which achieve that conductance. So this method will probably not lead to a big improvement unless the changes by itself will not lead to it. Yeah. So with that, I'll stop. Any questions?
Thank you very much, Piyush. Are there questions from audience?
Can I ask
Yes.
So, Piyush, I'm sure you must have already said this, but in the last multiscale decomposition for the log concave distributions, generally on convex domains. So, I thought when you were decomposing the convex domain using the Minkowski, right?
No, Whitney decomposition.
Whitney decomposition. So then each time the square represented uniform distribution on the square, right?
Yeah.
So now I can, if I have a density, I can say that restriction of that density onto that particular square, I can say that that will be the distribution.
Yeah.
So,
but this might not be a trivial problem anymore. That is the issue. So sampling from a cube, the uniform distribution of the cube is easy.
It's easy, which is why you are using that. I understand. Okay.
Yeah, but so here now you have to depend upon. So basically, instead of distance from the boundary, there's no boundary anymore in the log concave case usually. But you will have to say that I don't like. It will have to depend upon the local derivative of the log of the density, something like that. So basically, you want to say I want to only go as far so that so log concave distribution looks like e to the power minus fx, where fx is a convex function, right? So I only want to move so far that fx does not change by a lot. So the distribution in that slice is
highly non-trivial then.
Yes. So you have to make these kind of calculations, and then it becomes yeah.
Okay. And another thing is that when you said specifically, I'm sure you must have said it 100 times, but I haven't yet really understood where exactly is the convexity really playing the big role, apart from bottlenecks.
Yeah. Okay. So the thing is like almost everything will start breaking down. So for example, so in the station, so here, so the part I showed you, it does not. Okay. So somehow I have to prove isoperimetric inequality.
Right.
And here I'm using all kinds of things. So I'm using, for example, this picture, like these kind of pictures. For example,
those pictures I totally understand. The needle argument also will totally break down.
Yeah.
So I see. Okay.
So that's where the geometry.
I see. Okay. No, because I was thinking that if I have like some sort of very smooth domain, then I was saying that it should work, but because I do have
so maybe in this case, so here it might look a little more ad hoc because I'm saying I'm just decomposing across things. Of course, that requires convexity also. But for example, the localization lemma that I was talking about, that we don't use. I mean, we do use implicitly because one part of our proof is based on just appealing to older results. Right? If a lot of the body is inside, so that depends upon localization. So how does that proof go? So that actually goes by, as I would imagine, it goes by partitioning the body by hyperplane. So basically, I said there are two integral inequalities and they're both failing. So you try to say, okay, I'll half the body and still they are both failing on one, and you go like this. So this, of course, is presupposing.
Absolutely. Okay, thank you.
More questions, comments?
One more question. Sorry, are these tight? The times, the mixing times that you have obtained?
Yeah. So mixing time we don't know, but so according to that we are pretty sure it's not right. For the M infinity chain, the conductance is tight up to a logarithmic factor, log of n factor. So is it tight in the sense that there are sets for which what this says is the right answer up to a log n factor. But when you go from conductance to mixing time, there's a conductance squared thing, right? That does not necessarily have to be there. So that's why we can't say the mixing time is tight. So as far as I know, the mixing time might be better, but mixing time might possibly be better for the M chain. But for the coordinate, we are pretty sure it should not be tight because there are many losses. The comparison argument that you compare the conductance of two chains, that is almost, that is, it's design lossy. So there are huge losses.
Thanks.
More questions, comments? Okay, if not, let's thank Piyush again for this wonderful talk. Thank you. Thank you, Piyush. Thank you.
Thank you.
Thanks, Piyush.
You said it's used in informal now. You said it's used in algorithms.
What is this?
I think Sivaguru had asked where is
yes. So there are